So this is the second part of the structures of simple solids, where we're going to look at cubic structures. So the unit cells for the cubic structures, there are three of them that we're going to look at. The first one is a primitive cubic unit cell, this one on the left over here. And then we have in the center the body-centered cubic unit cell. And then on the one on the right over here is called a face-centered cubic unit cell. We're going to go through each one of them individually so that you get to understand exactly how atoms can be arranged in cubic structures. So to find lattice points, what are lattice points? Lattice points are those points that you would find on the corners of the cube. Okay, so in the first instance, we're going to look at a point that is completely inside the cell. It belongs entirely to that cell and it counts as 1. So if we look at this top diagram over here, you will see that we have one whole atom inside the cube, okay, and it sits in the center, and this would refer to a body-centered cubic cell. We'll get to the proper definitions shortly, okay. If a point sits on a face that is shared between two cells, okay, that cell, that atom contributes 1/2 to the unit cell. Okay, remember that there's another unit cell, another portion of the cell here, where the other half of the atom is now sitting on the face on this section over here. Okay, right over here. So that's when we have a atom or a lattice point on the face of the cell. Okay, for a lattice point that is on an edge, this is shared by 4 cells, and it will then contribute 1/4, where you've got 1 on each of the adjacent edges and on the 2 cells above. So if we looked at this diagram over here, you would see that this is the edge. There is a 1/2 and a 1/2, but remember there are 2 cells above. So that means that there are 1/4 contribution of 1 lattice point on that particular unit. Okay. Let me see if I can try and draw it over here, where you would have a look at if I had a lattice point on this edge there, like that. Okay, you would see that there are 4 cells, the one at the back over here, this one over here, this one that it's in, and the one below it. Okay, so that's how we contribute the 2 cells above and 2 cells below. All right, and then a lattice point at a corner is shared by 8 cells that can share the corner, and so the point contributes 1/8. If we have a look at this diagram on the left, you can see there's 1, 2, 3, 4, but remember that there are 4 equal cells above and below, okay? So that means that this point can contribute 1/8 of 1 whole. Okay, so let's look at the first type, which is a primitive cubic. The total number of atoms in a primitive cubic will be 8 times 1/8, so there's actually only 1, okay? So remember, if we look at, there is 1 on each corner, okay? There's a lattice point on each corner, so if we look at this diagram at the top here, we've got a lattice point here, 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 and here. There are 8 of them, but remember they sit on corners, so that means each one contributes 1/8, so 8 times 1/8 is equal to 1. Okay, we classify the lattice points at the origin over here, where we have this O, okay, as 0, 0, 0, so that means position 0 in the X, Y, and Z direction. Now, in terms of solid state, we represent the A would be in the X direction, B is in the Y direction, and C is in the Z direction. Okay, all the unit cells have 90-degree angles. The packing efficiency is 52.4%. I'm going to show you how we calculate that. There is a hole in the middle, so if we look at the structure at the top over here, you can see that there's a hole right there. Okay, the coordination number is actually in the cubic hole. Okay, so if we looked at this diagram that's labeled 1, 2, 3, 4, 5, 6, this is where the hole sits over here, and you can see that there are 6 lattice points that can go around that central atom, and something like octahedral geometry will probably be seen. Okay, we can also fit inside this hole, we can fit a sphere that is of 0.73 times the radius inside the actual hole. Okay, so that's what a primitive cubic cell looks like. If we are to calculate the packing efficiency, there's a number of ways that we can do it. Well, actually one way that we can do it. The calculation appears on the right hand side of the slide over here. I'm going to leave you to work through that one on your own. Okay, if the diagram is not very clear, I just want you to see that this distance here is the radius, so therefore this distance here will be the radius. So that means that the edge of the length of the cube is 2r. So the length here, this length side A, is equal to 2r. Okay, and so you can continue from that point forward. The steps in this procedure of calculating the packing efficiency is pretty straightforward. Okay, we can also calculate the size of the sphere that fits inside the hole. So this is one calculation. It's also not difficult to see. So on the right hand side here, you will see that there is a geometrical diagram that makes use of Pythagoras' theorem, and it works through, again, I want you to work through this whole mathematical calculation all by yourself to see that the radius you can calculate at 0.732 times r. Okay, let's move on to the second type of cubic cell, which is called the body-centered cubic. Okay, now you'll notice with the primitive cubic or the simple cubic, it had a designation P. Now we look and we see that we have a designation I. Okay, this is from the German word innenzentriert, which means centered inside. Okay, there are 2 atoms inside this unit cell. Okay, if we have a look at the top diagram over here, we have, remember, 1 on each corner. Okay, so that means 8 lattice points on each corner, which contributes 1/8 each. Okay, and then we have 1 in the center, which is this one over here. Let me just show you on the bottom diagram. That's the one in the center. So there's 1 full one inside plus 8 times 1/8. That means we have 2 atoms inside the unit cell. The lattice points at the origin are 0, 0, 0, and in the middle of the unit cell, it is 1/2, 1/2, 1/2. Now, how do we get that? Well, we move 1/2 in the A direction to here. We then move another 1/2 in the B direction to here, and then we finally move another half in the Z direction to give us the position of the lattice point in the center, and that's how we get the lattice points. Again, the angles are 90 degrees. The coordination number in this case is 8. Okay, the unit cell edge is 2.31 times the radius. The packing efficiency is 68%, and there is no central cubic hole, but there are other types of holes which we will take a look at later on. Okay, to calculate the packing efficiency in a body-centered cubic, again, the procedure is given to you on the right-hand side of the slide over here. You can work through that based on the diagrams and the geometry. It uses simple Pythagorean theory. You shouldn't have difficulty calculating the packing efficiencies of the body-centered cubic cell. And the continuation of the calculation is on this slide. Okay, the last cubic cell that we're going to look at is something called face-centered cubic. It has the designation F, and there are a total number of atoms in there calculated as 6 times 1/2 plus 8 times 1/8. So that is a total of 4 atoms per unit cell. So if I had to work that out, 6 times 1/2 is 3, and 8 times 1/8 is 1. So there's 4 atoms in total, or lattice points in total. How do we get that? Remember that the atoms on the faces contribute 1/2 because they are shared over 2 cells. And there are 6 of them. So if we look in the bottom diagram over here, you will see 1, 2, 3, 4, 5, and 6. They each contribute 1/2, so that's where the 3 atoms come from. And then the ones on the corner, there are 8 of them. So there's 1, 2, 3, 4, 5, 6, 7, and 1 at the back, which you can't really see. So that's where we get the total number of atoms being 4 for a face-centered cubic. All right. The lattice points are a little bit more tricky. So we have the one at the origin, which is 0, 0, 0. And then we have, because the ones at the faces count 1/2, you will see that in this case here, this one doesn't move in the A direction, but it moves a half in B and a half in C. Okay, and then this one here doesn't move in the C direction, but it moves a half in A and a half in B, and this one here moves a half in A, stays stationary on B, and moves a half in C. Again, the angles are 90 degrees. The cell lengths are the square root of 8 times R. The coordination number is 12. And in most cases, this is the highest type of packing efficiency that we can get at 74%. On this slide, I'll show you how to do the packing efficiency calculation. Again, it uses a simple geometrical arrangement, and it does the shows you how to do the calculation on the right-hand side over here. I want you to work through that by yourselves so that you can figure it out for yourself. It's a simple math problem. Guys, I'm your chemistry lecturer. I'm not here to teach you mathematics. Okay. Besides, you should have done stuff like this already. Okay, and then this slide is simply just a summary of all the cubic packing types, showing you the simple cubic or the primitive cubic. Remember, this is the primitive one. The body-centered cubic, which has the symbol I, taken from the German word Innenzentriert, which means centered inside. And then we've got face-centered cubic, or we'll talk about close packing in a later part of this unit. But the face-centered cubic, sorry, let me just erase that, is this one over here. It's the face-centered cubic, where it shows the packing efficiencies and it shows the coordination numbers.